This talk is about software architecture, and this talk is about code at the same time. And we can frame this talk very simply by this question. This is a perennial question I get asked all the time. Basically, do you have any decent tooling recommendations for pictures? And the answer is yes, but we'll come to that later. I live in Jersey and Channel Islands. Can you see it? Not really, it's a bit small. If this was one of those nice interactive touchscreens, we could do the pinch to zoom movement. Zoom in, still a bit small, and we can pinch it again. 9 by 5, 100,000 people, lots of sea around it. Why? It's a nice place. I previously worked in London, and I moved back to Jersey 6 years ago. And over the past few years, I've been kind of jetting around the world and basically helping people understand what architecture is all about. And this is my unique selling point. I want software architecture to be much more accessible to us as software developers. There are a number of ways I've done this. I have a course on parlays, if anyone's interested in that. And I have this book as well. And if you scan this code later on, you can get the book for a discount. In addition to talking about architecture, I still do write code. Phew, you're thinking. And this is really important because we have this kind of waffly, fluffily architecture thing up here, and we've got this low-level coding thing down here, and sometimes these two worlds don't quite meet, and that's the thing I'm really interested in here. It's the intersection between the architecture world and the code world. And my specific interest is diagramming and basically communication, and creating that shared vision that was mentioned in the keynote this morning. So let's talk about this tension between architecture and code. For those of you who have ever tried to create architecture diagrams to describe your system, you'll know it's really hard to do. And you'll know it's really hard to show everything on a single picture, because there are lots and lots of different things we want to show about our system. And when you read those classic architecture books, they talk about these things, views. You know, there's a logical view, and a physical view, and a development view, and all of these sorts of things. This is an extract from Philip Crichton's 4+1 architectural view model. And it basically says this: to describe a software architecture, we use a model composed of multiple views or perspectives. This is a picture of Philip Crichton's 4+1 model. Basically, there's a logical view, and that's components and fluffy things, modules. Then there's a development view, which is for us as developers, and it basically talks about how the code is organized to some degree. The process view is concurrency and that sort of thing, and then the physical view is infrastructure and hardware. And all of these things are coupled and brought together by use cases and scenarios. What we often see, and Philip's 4+1 model is one of a number of different view catalogs, is that the logical view of a system is often separated from the development view, in other words, the code aspects. And you'll see this if you go and look at lots of the other architectural viewpoints. Something I've been doing a lot over the past few years is jetting around the world and basically helping teams draw pictures. You did hear that right. I teach people to draw pictures. And it's really, really hard. So drawing pictures of software systems is a really, really hard thing to do because we don't teach it anymore. What's the purpose of these pictures, regardless of how we're drawing them? It's to answer questions like this. You know, if we're drawing a picture on a whiteboard as an upfront design exercise, that's the question we're trying to address. Here's a system, is that really what we think we're going to build? And if we're retrospectively drawing pictures of our system, then it's the other question. Here's a picture, does this picture reflect what we have in the code? Now, let's imagine you inherit an existing Java system, and let's say it's 100,000 Java classes. Would you draw a diagram to describe that system that included 100,000 boxes? No, of course we wouldn't. That's a silly idea, Simon. What would we draw instead? Well, we use abstraction. So when we're drawing architecture pictures, we're using abstraction as a way to chunk and group things together so that we draw a smaller number of bigger things. Abstraction lets us manage complexity. It lets us present a simplified view of the world. When we talk about architecture, what are we talking about? What are we referring to here by abstraction? Well, these are your modules, your components, your services, your layers, your subsystems. These are various techniques and methods we use to group stuff together. So abstractions are really useful. Without abstractions, we'd basically be stuck in the chaos. And here's a really interesting question. Imagine you go back to your office next week, and you draw some architecture pictures. And those architecture pictures include abstractions, modules and components and services and layers. And then you open your laptop and you look at the code. Do the two worlds match? Does your code reflect truly the things you've drawn on your diagram? Who thinks this is the case? There are some people laughing at the front and one hand at the back. Brilliant. I see lots of people drawing architecture pictures of existing systems, and if the diagrams don't match the code, what's the purpose of the pictures? They're just lies. It's just the fantasy of a system we want to build, but we know our system's a bit cruftier underneath. Why does this happen? It happens because when we're drawing these architecture pictures, we're using abstractions. We draw a box, we label it service or component or module or layer. In Java, is there a component keyword? I've not found it, but I don't think one exists. Is there a service keyword? Is there a layer keyword? No. So we refer to these types of abstract concepts when we talk about architecture, but they don't exist in the languages we use. The same goes for C#, Python, PHP, Ruby, blah, blah, blah. For anybody who came to Sarah's talk in this room in the last slot, Sarah talked about vestigial aspects of our systems. In other words, things that are just kicking around because, well, that's the way we've always done things. I'm going to throw layered architectures into that bucket. Maybe controversially, we'll see in a second. So, we're building a Java web application. A common way to do this is to use a horizontally layered architecture. And what I mean by this is we organize our code by a related thing. So we often have a package, that's our web controllers. We have a services package with business logic, and we have a kind of data access or repository type package for our data access layer. Quick show of hands, who does this sort of thing? Right, it's a good chunk of you. It's not everybody, which is really pleasing. Now, the whole purpose of this layered architecture is, well, separation of concerns. We can do mocking and testing and substitution and all that good stuff. And when we create these layered architectures, we normally have these rules. And our rules say things like, our controllers will only call one level down, and our business services will only call one level down as well. What happens in reality? You know what happens in reality. Imagine we want to add feature set C, and it needs bits of A and bits of B. We've got a whole bunch of ways we can do this. Now, when you're creating these layered architectures in Java, in order for, so let's imagine that one layer equals one Java package. In order for one layer to call something in another layer, the classes have to be public, don't they? So we make lots of our system public so we can jump across packages. And that's why lots of options are left open, and that's why, therefore, lots of systems, they start out with this nice clean layered architecture, but they quickly turn into the big ball of mud. Ports and adapters, hexagonal styles of architecture, slightly different way to organize the code. These are still basically layers. We just move the interface to a different part of the code base. Are layers important? Why do we describe our system as a bunch of layers? We like cakes, we like lasagna. Are layers important, or are layers just an implementation detail that we shouldn't really care about? Well, there's another way we can organize our code. We can organize it package by feature is another alternative here. So basically what this means is we have like a single Java package for everything related to feature set A, ditto for feature set B. We still have a layered architecture, but our layers kind of live inside those other packages now. So we've flipped the thing on its head. Layers are now our secondary organizational structure. Does this solve the problems of messy systems? Not really, because if we want to introduce feature C, that needs bits of A and B, the same thing happens. So what this is really about is it's about architecture on one side of the fence, and on the other, it's really about the architectural views. In other words, the way we describe our systems. And the architecture view of the world doesn't quite match the code. Now, George Fairbanks, a book called Just Enough Software Architecture. Fantastic book if you're really interested in software architecture. He calls this the model code gap. So in other words, there's a gap between our model of a system and the system itself, the code. And it's the same thing. Basically, we use all these nice abstract constructs up here, and down in our code, we don't have those things. Right. So let's backtrack a second. Why in 2015 am I still drawing pictures manually? Probably with tools like Visio. Why don't we just auto-generate these damn pictures? Has anybody tried this? What happens? Yeah, you just get this horrible big mess of stuff. These diagramming tools, and there are lots of them, some are diagramming tools, some are static analysis tools, they also suffer from the model code gap. The diagramming tools, when you point them at a code base, they see top-level packages, sub-packages, and all the classes. So if you point these diagramming tools at a large system with lots of packages and lots of classes, basically that's what you get in the picture. And yeah, you just get this explosion of stuff. The diagram looks a mess. I know I've got a mess, that's why I used a tool. But it provides you no benefit whatsoever. And there are lots of tools out there and you get pictures like this. Right, so this is the problem I'm trying to solve single-handedly. Wish me luck. Let's backtrack a second. How do we describe a software system? Maybe we should fix that first, and then once we have a good way to describe a software system, maybe we can fix some other problems as a result. Who's using UML here? I'm going to say that's about 10%-ish. It's not many people. UML is, a standard formalized notation, and it should be the one way that we all describe and share information about our system, but that's turned out not to be the case anymore. UML gives you a standard set of abstractions and a standard set of notations to represent those things. And both sides of that coin trip us up. I think a common set of abstractions is way, way more useful than a standard notation. This might sound a bit foolish because it's reversing what UML has done in the past, but bear with me for a second. Let's go and get two maps of London and lay them out side by side. The two maps of London will show the same things, won't they? The various districts and areas of London, the River Thames, the tube lines, the major routes and roads and bus routes, and sites and points of interest. So the maps are showing the same things, the same abstractions, but they might use different colors. They might use different symbols. Differing notation, same abstractions. How do we decipher a map? There's a key in the corner. Right, let's do that. Let's create diagrams that are self-describing. So let's push the notation question to one side a second and say, well, what are these abstractions we should think about? So this is the way I do it. I think of a software system as being made up of a number of containers. A container is something that you either host code or data inside of. In real terms, it's an app on a mobile device, it's a web application, it's an application server, it's a standalone program, it's a Windows service, it's a database, it's a file system. Something that needs to be running for your system to work in its entirety. If I kind of open the lid on my containers, I think of my containers as being made up of components. Now, this is a slightly overloaded word, so we have to be a little bit careful here, but actually we can use this to our advantage. For me, a component is basically a bunch of related stuff with a nice, clean interface. It's about modularity, it's about boundaries, it's about encapsulation. And because I mostly deal with Java, my components are made up of classes. And we're done. System, bunch of containers, those things contain components. Components are made up of classes. It's a really, really simple tree structure, a hierarchy, to describe the structural elements of a software system. With this in mind, we can then draw some pictures. And this is what I call my C4 model in my book. We can have a system context diagram, which is basically your system and stuff around it. We then do the pinch to zoom in movement, and we show the containers. This is the web app talking to the database and whatever. We then zoom into a container, and we see the components inside it. And optionally, if we really want the low-level detail, we can do the final pinch to zoom movement and see the classes. Quick example for you. When I moved back to Jersey, I basically built this as a content aggregator. It lists local tech people, tech businesses, blog posts, events, and jobs. It's called techtribes.je. This is a system context diagram for my system. That monkey thing there in the middle is my system. There are a bunch of different types of users and a bunch of system dependencies. So we're pulling profile information from Twitter, blogs, and stuff from GitHub. If this was a Google Maps interface and we did the pinch to zoom movement on the monkey's head, we open up the monkey. This is the containers diagram for my tech tribe system. People at the top, systems at the bottom, everything inside that red box is mine. There's a web app at the top, Apache Tomcat, that's the key point of access for all the users. There's a standalone process at the bottom. It's the thing that reaches out to Twitter, GitHub, blogs, pulls data back, and all of that data is being stored in that middle trio of boxes. There's a MySQL database storing that stuff. There's a MongoDB store storing tweets and blog posts, and there's a file system in the middle. Doesn't tell you anything about clustering, standby, failover, redundancy. That's a different view. This is just the static structure. We take this one down here, we do the pinch to zoom movement, we see the components inside it. Everything inside that red box lives inside that standalone process. Because this standalone process talks to the outside world, I've shown those things on the bottom, and this process talks to a bunch of other containers for storing data in this case. And basically, this diagram just lists out the components inside that Java application. In the middle, there's a Spring scheduled task. It gets kicked off every 15 minutes, uses the various connectors to the outside world to pull the data back, and that data is stored in the various databases at the top. That's it. The reason I do the pinch to zoom movement on my intro is because these diagrams are basically maps. They're maps that help us navigate a large or complex software system. If you go to Google Maps on your phone and you do a search for Jersey, it will zoom straight in and give you that view at the bottom. This is fantastic if you want to know what's in Jersey and what the various place names are, but if you've never heard of it, it's pointless. And you have to do the pinch to zoom out movement to get to the map of Europe at the top. The diagrams are the same. Sometimes as developers we want the zoomed in, the low-level view of the world, and sometimes we want to zoom out and show the higher pictures. Now, I'm not saying that you should only draw these types of pictures because there are lots and lots of other ways you want to describe your software system. You might want to show behavioral and runtime things. You might want to show the UI mockups. You might want to show the core domain models, infrastructure diagrams, deployment models, all of that sort of stuff. What I'm trying to do is create a very simple static model of my system that ranges from the classes through components, containers, and up to the system. And with that kind of static core in place, we can weave in other things around it. So for example, we can show sequence and collaboration diagrams that show interactions between components. We can show how our containers map to infrastructure. That's our deployment model, essentially. So this C4 stuff is about the static structure, which is basically about the code. So I'm trying to join these two worlds up. Why am I doing this? It comes back to what I said during my introduction. I want software architecture to be much more accessible to us as developers. And actually, I think we as developers are the most important, with the primary stakeholders of software architecture. We should probably answer the components question. I've been using the word component. I've shown you some pictures with components on, but what is a component? And specifically, what is a component in the context of a Java app? Who's familiar with Spring here? Excellent. So Spring, popular framework in the Java world. There's something called Spring MVC. Spring MVC is a web app framework. on GitHub, there's a sample application called Spring Pet Clinic. And it's a demo application that shows you, a good way to write a Spring MVC web application. This diagram down here on the left is the architecture diagram that the Spring team used to describe the system. And it's basically a layered system, a layered architecture. A bunch of browser stuff here, some controllers, some services, some repositories, and we're done. If you download the code, that's what the right screenshot shows. So there are a bunch of model classes, entities, domain classes, that sort of thing. There are some repository things here. That's your data access objects. This clinic service, which we'll come to later. Some utils, because we've got to have utils. And there are some web controls at the bottom. All good so far? Imagine this is your new project. And imagine you want to get to grips with how this system works and how all of these elements fit together. What's the easiest thing we can do? Well, we can load the code into our IDE, and we can ask the IDE to draw some pictures. And lots of IDEs have this ability to create a UML class diagram of that stuff. So this is what happens if you do that. Now, I have been criticized before, because when I've shown this, people have said, Simon, you should have spent at least 10 seconds dragging the boxes around to make the diagram look prettier. It's impossible, right? I spent ages trying to do this. It's impossible that I just show this picture now. There are too many boxes and too many relationships. Don't forget, this is a small sample app with, 20 or 30 classes. Imagine your 100,000 class monolith. Your IDE would probably crash at this point. So this is not a very useful diagram. How can we make this more effective? Right, let's ask a different question here. Given that set of classes on the right, how about we draw a picture of those things that are structurally significant? So let's try this now as a group exercise. The model classes, the domain classes, the entities. Show of hands, who thinks they are structurally significant? A couple of people, but mostly not. What about the repositories, the data access objects? Structurally significant? I think so. I mean, that's what this diagram down here says. The service, when you open up the service, it's quite structurally significant, and you'll see why in a second. The utils, are the utils structurally significant? I hope not. We've got real issues if they are. And the controllers, I'm going to say, are structurally significant. So if we take this approach and do some filtering on the UML class diagram, we can draw something that looks like that. Do you see the layers coming back in here? We have our layer of controllers at the top. We have our layer of repositories at the bottom. And in the middle, we've got this weird fan-in, fan-out thing. And that's the clinic service that hooks everything together for some reason. I don't know why it was built like that, but it was. This is quite a nice, simple diagram. In order to present an accurate picture, what I've had to do on this diagram is show both the interface and the implementation class for the service and the repositories. So the interface shows you what services that thing provides. It doesn't tell you what it depends on. It's the implementation that depends on other interfaces. That's what we see by this picture. So what we've got here is, it's a nice simple picture, but this is a small system. And there's still a bit of noise here. This is still a very low-level implementation class and interface type diagram. What I really want to do here is kind of pinch zoom up one notch to get to components. And what I'm really looking to do is draw something more like that. So I want to collapse the interface and the single implementation class here and call it a component. Right, these are my reusable structural building blocks. And basically, I want a picture that looks like that. So this is the same thing, except we've done the collapsing of the interface and the implementation class. Controllers, service, repositories. And I want to generate that automatically as well. I'm going to set myself some targets here. So we're trying to get these two worlds to merge. Who remembers model-driven architecture from like 10 years ago or something? Who's still doing model-driven architecture? Silence. Tumbleweed. Model-driven architecture was this thing where you'd basically buy a really expensive modeling tool, you draw lots of really scary pictures. Inside your scary pictures, you put lots of code, object constraint language, bits of Java code, script, whatever it was. That was the behavior of a system. You'd press the magic button, and it would build your system. Yay. If you wanted to make a small change to your system, what did you do? Go back to the modeling tool, make the change, press the button, system pops out. Horrible idea. There are still a couple of industries using it, but for us building, web apps, business systems, it's not really suitable. So I'm definitely not going to suggest we do that. But I do want to draw pictures, and I want to draw pictures where the boxes on the pictures match stuff in the code. I do want this nice reflection both ways. Do you remember George Fairbanks? He calls this the model code gap. Well, George is a really smart guy. And further through that book, he says, look, all you need to do to fix this is adopt an architecturally evident coding style. An architecturally evident coding style is essentially dropping hints into your code base so that elements in your code reflect things in your architecture model. In concrete terms, this means stuff like naming conventions. So if you're building a component in Java, give the interface the word component somewhere in it. Maybe there's a packaging convention where everything related to a single component sits in the single Java package. Maybe you throw annotations onto classes to make them, to signify them as being architecturally significant or important. Who does this? Who proactively does this? There's a few people sort of going a little bit. It's one of those things that when you read the book, it makes a ton of sense. And I think unconsciously we probably strive to do some of this, but it's not something we do as an explicit practice. My little Tech Tribes aggregator. So on the right here, we have the component diagram for the standalone content updater. And in the top right corner, there's this thing called a tweet component. And the tweet component essentially puts tweets into Mongo and gets tweets out of Mongo. It's just a boring CRUD component. It doesn't do anything exciting at all. So we can ask me this question. Given my source code, which is all on GitHub, and the diagram I showed you, is there a nice mapping between the diagram and the code? So in other words, can we find something in the code that is called a tweet component? And the answer is, drumroll, yes. Because I am that 10x rockstar ninja developer they talked about in the keynote. Thank you. See, look, tweet. Now, I'm actually not that 10x rockstar ninja developer because, do you know what? It didn't actually start out matching. So the initial implementation of my Tech Tribe system was a traditional layered architecture. It's one of those vestigial things that we kind of do because we've always done it that way. So what did I have? Well, this is a Spring system. It's a web app with Spring MVC. And I had a services layer, a services package, with a bunch of different services in. One of them was the tweet service. And I had a separate package for my data access objects. And there was a Mongo implementation in there for my tweet data access object. Fairly common pattern. Where's my tweet component gone? Doesn't exist. The tweet component is really a kind of logical, fluffy grouping of two things in two different layers. Do you see what I've done here? This is a great example of the model code gap in action. My diagram says one thing, there's one box for tweet component. My code says something completely different. How do we fix this? Two options. Option number one, redraw my pictures. Can't be bothered, too hard. Do you know why it's too hard? Because now I've got twice as many boxes to draw. Option two, refactor. And that's what I did. So how do I refactor this to look like components? And the answer is very, very simple. This is what I do. It's called package by component. And essentially what I'm looking to do is put all of the things related to a single component in a single Java package. In concrete terms, this means merging the service layer and the data access layer together in the same package. So the actual implementation that I have now, and you can go and have a look at this on GitHub, is this thing over here on the right. It's a really, really simple, trivial refactoring. So that's my service interface. It's now over here. It's been renamed to be tweet component. I like that. Now the naming matches. No changes aside from that. My default tweet service, which is horribly named, is now tweet component impl, which is equally horribly named, but it's package protected, which means it can't be seen from the outside world. That's kind of nice. My Mongo tweet DAO is basically up here, almost unchanged. That's also package protected. Because we've now got both layers in the same component, I'm going to ditch the interface. I don't need it anymore, because in Java you can't have non-public interfaces. So this is what it looks like. This is a screenshot of IntelliJ, the code loaded into IntelliJ. That's my interface. I've also added an annotation, a custom annotation, which says this is a component, and that's what the code looks like. So there's my interface, there's my implementation class, there's my DAO, and I've got my Spring config all bundled up in one Java package. And I've taken that same pattern, that same architecturally evident encoding style, and I've applied it to the rest of my system. So that's one option. There are a bunch of other ways we can do architecturally evident encoding styles. We could use annotations and attributes. So for those who are doing C#, you've got the same thing in that language. Naming conventions, of course, and this is something you can apply to older code bases. Namespacing and packaging conventions, that's something I've done here. Maven modules. So if you're using Maven modules, maybe each Maven module is a component. OSGI is another way to create an architecturally evident encoding style. So you have a bunch of boxes on your architecture diagram, and each box is an OSGI module, OSGI bundle. Jigsaw stuff. Super excited about Jigsaw because hopefully we're going to get some modularity stuff, some constructs into the Java language. Again, that's another great way to create an architecturally evident encoding style. And microservices. If you think about it, microservices is an architecturally evident encoding style. If we were to draw out a microservices architecture, it's a bunch of boxes with connections to a messaging bus or sending REST requests or all over the place, for example. And each of those microservices hopefully corresponds to one thing in the code. One IntelliJ project, one repository on GitHub, whatever it is. This has some implications. Testing is one of them. So if you remember back to my picture I just showed, I said I removed the data access object interface. And this now kind of makes it a bit harder to mock out my Mongo tweet data access object and test my service in isolation. And that's one of the other vestigial things I think we do as software developers. And this is our typical testing pyramid. This is a quick aside, but it's kind of an interesting aside. And we're taught to do lots of unit tests, and we do mocking to make them really fast. We have these slower running, often broken and brittle integration tests, the things we usually put @ignore at the top of. Yeah, we've all done it. And then you might have some acceptance and system tests at the top. What's a unit? How big is a unit? When we're writing an integration test, what is it we're integrating? Are we integrating classes, or are we integrating our thing with the database thing? These terms are just nuts. These terms are so ambiguous, and every team has a different definition of these terms. We could use the architecturally evident coding style to maybe reboot the testing terminology. And this is something I wrote on my blog earlier this week. So I'm a big fan of maybe renaming some of the tests to align with the architectural constructs that they're testing. So maybe we have a bunch of class-level tests that do all that low-level stuff with mocking and really fast test runs. And then maybe we have some components or service-level tests that test through the public interface. And actually, that's what I do with my tweet component. So I don't unit test in the traditional sense, my tweaked component. What I do is I write a bunch of component tests that spin up Mongo, throw some data in, and test through the public interface. I can get a lot of coverage by writing a really small amount of code. I like that. And then we have the system tests on top. These are your kind of big, outside-in, test the whole system. It's an interesting aside. And there's an interesting relationship here between how we structure our systems and how we test our systems. Have a think about that. Yes, so now we get to the title of this talk. Software architecture as code. So the code is the embodiment of the architecture, isn't it? The code represents the final realization of some architectural intent we had a while back. So we can ask this question. Is the architecture in the code? Can we somehow scrape a definition of the architecture model from just the raw code? This is a paper by Paul Clements from 1996, I think it was. And it's a paper about architecture description languages. And he says this: in practice, architecture is embodied and recoverable from code. I don't think this is true. I think it may have been true in 1996, given the languages that were being used, but given the stuff we're building today, I don't think you can extract a sufficient architecture model from an existing code base. Let's try this out. Let's imagine we want to draw a context diagram of your system automatically. The context diagram shows users and people and systems, system dependencies. Can we get an accurate list of people from your code base? Maybe. So if we're building a web app, maybe parts of our web application are accessible to different types of users, maybe we can automatically scrape the security configuration to extract a list of different roles and user types. Maybe we have a bunch of enumerations in our code base that list out the types of users explicitly, but I don't see people doing this often. So the list of people is kind of hard to get. What about software systems? Can we accurately get a list of systems that our code base integrates with? It's kind of hard, isn't it? It's kind of implicit. So we could look for known libraries. So with my Tech Tribes example, I use Twitter for J because I'm using Twitter. So we could have a bunch of rules set up that say, if you see Twitter for J, then assume that we're using Twitter. We could look for known API endpoints. So we could have a set of target URLs to scrape from the code base. That might work. What about those nasty situations? And don't laugh, because you will do this at some point. You drop a file on a file system, and another system picks it up. It's like that horrible implicit integration mechanism. Can you get that from the code? No. So that top-level picture is really, really hard to draw from just scraping stuff out of the code. Pinch to zoom in, containers. Can we get an accurate list of mobile app, web app, database, those things that make up our system? Maybe. Imagine we've got a Java system, and it's all in one IntelliJ project file. Maybe we could write some code to scrape the IntelliJ project file, look for web apps, look for public static void main apps, look for references to Docker. So we could potentially scrape some useful information out of the code, but that's also quite hard to get. Pinch to zoom in. What about components? Can we get an accurate list of components from a code base? Yes, if we use an architecturally encoding style. In other words, if we've been explicit about defining what a component means to us in the code base, we can then use those rules we created to scrape stuff out of the code base. So what I'm trying to do here is essentially this. I'm trying to extract as much of the architecture as I can from the code base and supplement it with the stuff I can't. And what I've done to do this is I've created an architecture description language using actual Java code in this case. And here's a quick example. So this is a bunch of Java code, and I'll show you, we can grab this later. This is a bunch of Java code that expresses and describes the architecture of the Spring Pet Clinic system in Java. So there's some boilerplate stuff at the top. We create a model to work with. These next 3 lines, we're going to create the Spring Pet Clinic software system, and we're going to create the clinic employee. That's the one type of user who uses this system. And we're simply going to wire these 2 things together. Clinic employee uses the Spring Pet Clinic system. Brilliant. That's the top level picture done. Step down, containers. What is the Spring Pet Clinic system? It's basically a web app talking to a database. So let's just model that in code. Let's create a web application. Let's create a database. We'll say that the clinic employee, the user, uses the web app. That's the interaction between the user and the web app. And we'll say that the web application uses the database. That's basically sufficient to model the containers level description. I don't want to have to do this for the next level down because there are, 10 components, and it's going to get really tedious really quickly. But it's code. So why don't we just scrape that stuff out of the code? And what I'm going to do here is I'm basically going to say, look, with Spring MVC, you add annotations to classes, at controller, at service, at repository. So let's use that information, scrape the code base using reflection, and extract those annotated classes. So that's what I've got here. I've got a Spring component finder, and it basically pulls out my controllers, my service, my repositories. And it also does some static analysis and looks for all the dependencies with them. It also collapses the interface and the implementation class and gives me a reference to a component back. I also want to scrape the Java doc. I want to scrape, in this case, the top-level Java doc from the interface and use that to populate my architecture model. So I'm trying to get as much information as I can from the code. These next few lines here, basically what I want to do is I want to say, look, the clinic employee, the user, is using all the web app controllers, and the repositories are using the database. So that's kind of fleshing out the top and bottom of my picture. So that's the model created. I then need to create some views to visualize this. And these things here, this is basically a programmatic way to describe those C4 diagrams I showed you before. So there's a context view, which is all software systems and all people. There's a container view, which is all people, all systems, all containers. And then I want to draw a component view for my web app. What I'm also going to do is I'm going to make an explicit link between a component and the source file for that component. And I'll tell you why in a second. So all of that stuff is called Structureizer for Java. It's all open source. It's all on GitHub. It is a work in progress. And there are various component finder strategies you can use to extract useful things from your code base. You can get that open source library to output JSON, because we like to JSON everything. But JSON's not going to give you pictures. So what I've also done is I've created some lightweight tooling, some web-based tooling to draw some pictures. This isn't open source, but you can go use it for free. And if we throw that model up to my Structureizer tool with a web API, these are the diagrams it generates. So this is my context diagram for my Spring Pet Clinic system. Employee using the system. Boring, but that's all the system is. This is my containers diagram. It's the employee using the web app talking to the database. Again, all of this stuff was in the code I just showed you. And that's the component diagram I showed you before. So it's pulled all of the components and the Java doc and wired everything together. That's the Spring story. Spring's nice and easy in that respect. I'm trying to do the same thing with Java EE. So I've taken Aaron's Java EE 7 hands-on lab, and I'm trying to create a bunch of Java EE component finders to extract Java EE components from my code base as well. This is what happens when I plugged my own tooling into my TechTribes web app. It sort of looks a bit of a mess. Now, I can explain this picture to you, but I shouldn't have to. All of these things along the edge are my Spring MVC web app controllers, and they all use my package by components, because actually there's some common information on every page, and that's why there's this nest. How useful is this diagram? Not very. But this isn't a diagram in Visio. It's a model. It's a model of the system. And because it's a model and because it's written in code, we can write more code to slice and dice the model. So, for example, it's really trivial to do stuff like this. Go and find me all Spring controllers and then create one component view per controller. So rather than showing the whole web app, we're showing a vertical slice at a time. And basically the net result is this. You get a larger number of really simple pictures. You throw that into your build system, guess what? You get living, breathing architecture documentation. Yay. So I've dragged architecture back down to earth and made it meet the code. Why did I link my components with the source code? Because in my tool, if you double-click a component, guess what it does? It takes you to the source file on GitHub. So again, we've got that nice traceability all the way through. Oh yes, good point. What is the point of all this? People moan at me that their systems are hard to work with. Well, change them. Right? You own that responsibility. And the maintainability of a system is inversely proportional to a bunch of things, especially things like public classes. I think a good architecture actually gives you agility. So if you want to move fast, if you want to react to change, you need to create a good architecture. And agility is a quality attribute. It's a non-functional requirement that we need to take into account. And of course, there are different ways we can build systems. We've got monoliths on one side. You plow everything into that single deployable unit. Nice and easy, quick to build, quick to deploy, but if you want to make a tiny change, you have to redeploy the whole thing. And sometimes these end up being that horrible big ball of mud. Other side of the spectrum, microservices and service-based approaches. Lots of agility, lots of flexibility, but more complexity. And there's lots and lots and lots of hype currently over at the microservices end of the spectrum. Martin Fowler published a blog post last week basically saying, look, maybe you should start with a monolith and go to microservices if you think that's a good idea. And I agree. We can still build monolithic systems with nice, neat component boundaries inside them. That's why I'm really excited about the Java 9 Jigsaw stuff. It's about putting components and modularity and boundaries back into monoliths to essentially create structured modular monoliths. And if you can't do that, don't do microservices. Right, that's my honest advice here. If you can't build a nice, neat, structured monolith, don't bother with microservices because you're just going to create a distributed big ball of mud. For me, having those nice, neat components inside your monolith is a fantastic stepping stone to microservices. You carve up your monolith in nice chunks. You find a use case where you want to take a chunk out and spin it up as microservices. You do that. You carve it out, you throw it into a microservices container, you're done. So my closing thoughts here are basically think about how to align the software architecture view of the world with the code. How do you do this? Keep the architecture model in your head at all times. Be conscious of it and try to explicitly adopt an architecturally evident coding style. The best advice I can give you right now is to stop making every class public. But this is hard to do. And lots of frameworks force us to use this keyword. It's also muscle memory. Whenever I do file new class in IntelliJ, it puts public in there. Or I type public class for some reason. I can't fix that. I can only give you an incentive to change your behavior, and that's the incentive. Charity jar, pound in every time you write public class without thinking. Right, start using Java's access modifiers properly until we get the Java 9 module stuff. If our software architecture model is in the code, if we've created a nice modular system, then we can extract that information out of the code, and a whole bunch of other stuff becomes nice and easy. And my key summary point is this. Just think. Challenge everything you're doing, and go from there. Thank you very much. So I think we're at 10 to 5. That says 2 minutes. So I reckon we can have a minute's worth of questions, if there are any. So do I have the right page, and are there any questions? Any questions in here? Yes?
So you've got the code there to automatically identify components from Spring annotations.
Yeah.
Easily extensible to use some other if you've got one.
So the question is, I've got a component finder that extracts Spring components from a code base. How extensible is that mechanism? And the answer is it's all open source, and you can do whatever you want. So I'm using a static analysis framework to load the metadata from the built version of the app into memory, and you can slice and dice it however you want to. So I've got component finders based on naming conventions. I've got the Spring stuff. I've got component finders for my own custom annotations, doing the Java EE stuff. So yeah, that's why I open source that, because that's the complex bit. That's the bit that needs to be customized for everybody's system. One more question, if there is one. Yeah.
Have you got an opinion on the balance and benefit of modeling a process on then communicating the system post-construction?
So do I have a view on modeling as a process and then communicating that vision afterwards? Is that the question?
Well, the balance and benefit.
The balance and benefit. So my personal way of doing this is basically do a small amount of upfront design, do some sketching on a whiteboard down to component level, and then start writing code. And then how do we keep those diagrams up to date? You use something like my structurizer tools to automatically generate that stuff. So for me, that's a nice balance of upfront design plus living documentation. The thing's flashing time up now, so I think we should call it a day. Thank you very much again.